We are group 25 and we are going to present implementation of such algorithms for FPGA routing and placement. First is the genetic algorithm. This algorithm is crucial as it employs a very nice way to see the difference between the different iterations that we come across as the algorithm progresses through the different generations from parents to children. So let us dive into this algorithm. We have presented this code to minimize the wire length required for FPGA placement and routing by means of a search using the genetic algorithm. So central to this code is the chromosome class. Each chromosome represents a potential solution to the problem and includes two main attributes, placement and routing information. Additionally, a fitness score is associated with each chromosome. So as you can see, we have various functions in this algorithm. For example, we have used the initialize population function. Next, we have used the evaluate fitness function. And then the genetic algorithm employs three parent selection methods: ornament selection, ranking selection, and Rowlett wheel selection, which determine which chromosome become parents for the next generation. Also, we have implemented the crossover function, the mutate function, and the run genetic algorithm function finally, which ensures that all these characteristics of the genetic algorithm can be run and tested. We also have a display chrome function, which shows our final results after running the algorithm with each test case. Now we move on to the comparison of configurations. And as we can see, in the compare genetic algorithms function here, we have different parameter configurations which correspond to the population size, max generations number, mutation rate, number of parents, number of children, number of nodes, number of edges, and the parent selection method. So in our first test case, our first configuration, we have the parameters as 10, 10, 0.01, 5, 5, 6, 20, and tournament respectively. For the second one, we have them as 10, 10, 0.01, 5, 5, 6, 20 with a different parent selection method, this time as ranking respectively. And for the last one, we have all the parameters same except for the parent selection method, that is Rowlett wheel this time. So we want to compare how the algorithm results differ when we change the parent selection method each time. So we have this GUI mate, which displays the result when we run each test case on this algorithm. Let's see. So as we can see, all the three parent selection methods with the same set of other input values are run. And here an analysis has been presented regarding what configurations, how many generations, what was the mutation rate, number of parents, number of children, number of nodes, edges, and the parent selection method each time. So since it also has an aspect of randomness into it, so the solution fitness may be zero at times, but it depends each time how the algorithm runs and what the random moves are made in the algorithm. So here we have them presented for each case. And for this one, as you can see, the Rowlett wheel parent selection method is proven to be the best. However, it depends from run to run and may differ. So this was genetic algorithm. Thank you. Now we present particles from optimization for FPGA placement and routing. So this code has many different classes like particles and PSO. It also has functions such as generate random position, calculate fitness, update global best, update particles based on weights like cognitive weight and social weight, run PSO to finally run the algorithm, and draw block to finally provide a visual representation of our final routing and placement result obtained by running the algorithm. So PSO, as we know, is inspired by nature and it models the behavior of a particular member in a swarm based on the behavior of the other members of the swarm. So the core of the PSO algorithm is the particle class, as you can see. Each particle represents a placement solution with attributes for position, velocity, best position found, and fitness based on placement quality. Particles are initialized with random positions and velocities to introduce diversity and exploration into the optimization process. The fitness of each particle is determined based on the quality of placement, aiming to maximize fitness as by evaluating the particular fitness function, and its higher value is better. The PSO class is responsible for coordinating the PSO optimization process, initialized with parameters including the number of particles, nodes, edges, maximum iterations, and others. The global best function in the PSO algorithm is meant to maintain a global best position and fitness score, updating them as particles explore the solution space, ensuring the best solution found is recorded. Particles' positions and velocities are updated using a combination of inertia, cognitive, and social terms, guiding particles towards better solutions while maintaining diversity. Finally, the PSO algorithm is executed using the run PSO function for a specified number of iterations. During each iteration, particles are updated and the best solutions are visualized on the FPGA grid, as we will see. The global best position is also updated. The draw block function visualizes the component placements on the FPGA grid. It uses canvas element to draw rectangles and tables for each block. So now we will run the code and see a comparison of the different test cases which are run on different configurations generated randomly in course of the running of the PSO algorithm. However, the initial parameters in each run that we give, which are the number of particles as 5, number of nodes as 3, number of edges as 20, maximum iterations as 10, remain the same. So now let's run the algorithm and see the result. So as we saw, the different placement of the individual components of the FPGA grid through the course of each iteration that we came across was shown in a quick manner on the graphical interface GUI that you can see. Similarly, the best solution here is displayed, including its fitness and the best solution placement, since we gave 3 nodes. So the probability of the involvement of the particular node in the placement process in each case is displayed here using the results, and the best solution fitness for a particular configuration is given here. For this one, it was 93.96836. So this was the PSO algorithm for FPGA placement and routing. Thank you. Now we look at the coin optimization, ACO algorithm for FPGA placement and routing. So in this code, as we can see, our aim is to minimize the cost that's required for the task of FPGA placement and routing. Our algorithm uses classes for FPGA representation, and that explore the FPGA functions for updating pheromones, evaluating solutions, and visualizing the results. FPGA class represents the FPGA grid with attributes for width, height, the number of tracks, grid representation, and obstacle placement. Provides functions to place obstacles on the grid, as we'll see. The AND class simulates an AND's behavior, where each AND represents a potential placement solution. It can move on the FPGA grid and its placement is recorded. So our update pheromones functions, which are update pheromones logic 1 and update pheromones logic 2, have a different pheromone deposit rate as 0.5 and 0.1 respectively, which will impact how the algorithm progresses. Then next, our evaluate solution function calculates the cost of a given placement solution based on the pheromone levels on the FPGA grid. The visualize FPGA routing function provides a graphical representation of the FPGA placements and obstacles. The plot wire length function plots the wire length and shows its evolution during the optimization. Now we'll move on to the different test cases that we are going to use on each of these pheromone update logics 1 and 2 with different deposit rates of pheromone. So we'll have two cases, more ANDs and less iterations, and then as you can see, less ANDs and more iterations. So these two test cases try to capture the impact of having more iterations and the impact of having more space being used versus the impact of less iterations or having less space used. So let's see the implementation of this code. So now if we go to logic 1 of pheromone update with a pheromone deposit rate of zero point 0.5, it's 0.1 for logic 2. And as we can see, the while length versus number of iterations for logic 1 and logic 2 of pheromone update for the case of more and less iterations has been displayed here, where we see a more increasing trend for one logic compared to the other for the while length that is required as the number of iterations increased is shown. Similarly, here we have the logic 1 pheromone update placement and routing result, which has a deposit rate of 0.5 again. And this is again for the same case of more and less iterations. Now we have the pheromone update logic 2, which has a deposit rate of 0.1. And here we can see for the same case of more and less iterations, what FPGA placement result diagram it finally gives. Now we move on to the second test case, that is having less and more iterations. And here we see its FPGA placement and routing diagram result for the pheromone update logic 1, which has a deposit rate of 0.5. As we can see. And again, we have the graph of while length versus the number of iterations for this case of less and more iterations on implementing both the pheromone update logics. That's with a different deposit rate of 0.5 and 0.1. So as we can see again here, logic 1 of pheromone update gives a more increasing trend of while length with the increasing number of iterations than logic 2. And as you can see, the again the pheromone update logic 2 with a deposit rate of 0.1, the placement and routing results for the case of less and more iterations is presented here in this FPGA diagram. And here we can clearly see the results displayed in a statement form. So for the case 1 with more and fewer iterations, we have the final while length for pheromone update logic 1 employing a deposit rate of 0.5 as 20417.53, while the same for logic 2 using the same more and less iterations case is 19102.982. This logic 2 with a lesser while length is better. Similarly, we see case 2 of fewer and with more iterations and the results of the while length required for each of the pheromone update logics. And we again find that logic 2 in this case proves to be better. However, this depends on the algorithm that we are using, and it may differ with the runs, like which particular path of the update and other steps are followed by the ACO each time we run the full algorithm. So this was ACO for FPGA placement and routing. Thank you. So here we present simulated annealing, that is SA algorithm implementation for FPGA placement and routing. So as we know, SA is a very good algorithm for finding near optimal solutions to many problems like this placement and routing problem. So our algorithm implementing simulated annealing includes functions for calculating wire length, performing SA, and visualizing results. The calculate wire length function here calculates the total wire length based on the Manhattan distance between placed blocks. It is a crucial metric for evaluating solutions. Next, the simulated annealing function takes an initial placement, temperature, cooling rate, and the number of iterations. It explores different placements and aims to find the best one. Also, the logic for including a solution worse than the others, that is making a bad move at certain higher temperatures initially, is given as a probabilistic condition, which is calculated in this if and else part of the logic. Next on, the plot while function is written, which helps us to visualize how the while changes during the assay process. It's an essential tool for understanding the algorithm's progress. So we'll explore different test cases with varying cooling rates. Each test case aims to find the best placement by adjusting the rate of temperature reduction. So as we can see, in test case 1, we set the cooling rate to 0.95, in test case 2 to 0.98, and in test case 3 to 0.99. We aim to understand the effect of a more aggressive temperature reduction strategy as we go on. We keep the number of iterations as 5,000 and initial temperature as 1,000. So now let's run the algorithm and see the results. So as you can see, for our test case 1 with the cooling rate of 0.95, this is the graph of while changes over the iterations as the algorithm progresses. Similarly, for cooling rate of 0.98, this is the graph, and this is the graph for cooling rate of 0.99. As you can see, all of them, all of the different cooling rates lead us to an almost similar trend of while length as the number of iterations go on increasing. However, the steps in which we reach to the final while length in each of the cases, the path the algorithm takes, that we can see by the initial part of the while length variations as the iterations progress, till say around to a value of 1,000 iterations, is different for each of the cooling rates, because this is greatly influenced by the number of bad moves the algorithm makes at the higher temperatures initially, which again depends on the cooling rate, that is how long the temperatures remain considerably high, thus giving us a different path each time. Similarly, here the results showing the best placement with the cooling rate each time have been displayed, and it has come out that the minimum value with a cooling rate of 0.95 or for a cooling rate of 0.98 or for a cooling rate of 0.99 has come out to be 12 in each case. However, it can be different depending on the run of the algorithm each time, the path it takes, since it has an element of randomness again. So we may get a case where the minimum value with each cooling rate turns out to be same. However, the individual placements in each of the cooling rate cases are different, as you can see. That's the coordinates of where the blocks are based on the FPGA gate. If you run the algorithm again, we get to see the results again this way. Again, the minimum value with the different cooling rates turns out to be same. However, the individual placements are again different for another run of the algorithm. This time, the minimum value with cooling rate 0.95 is 0 because the algorithm takes a different path to achieve the result. So as we can see, for this run of the algorithm, the minimum value length, the cooling rate of 0.99 comes out to be 8. This is better than that what we achieve with the other cooling rates of 0.98 and 0.95 this time. So it depends on each run of the algorithm what the result is. And we have to run the algorithm for a considerable number of iterations to obtain our desired results. That is the degree of optimality to the best solution which we want. So this was simulated annealing for FPGA placement and routing.